Okay, so up to now we were able to find out the maximum load acting on the slab and the moment, as well as we were able to find out the area of steel required for the slab, and we also calculated the spacing and we checked for maximum spacing. So after doing all that, we have to also provide checks. There are mainly three types of checks. The first one is the deflection check, the other one is development length check, and lastly the shear check. Okay, we will go through all of this. So first we'll proceed with the deflection check. So this is given in the clause number 23.2.1 on page number 37 and 38. For this we have to use a graph. I'll show you quickly how it is done. So first we have to find out the value of Fs. Fs is equal to 0.58 Fy into AST required upon AST provided. This formula is already given in the IS code. If you read the clause number 23.2.1, you will get the formula there. It is just below the graph. I'll show you the graph later on. So if we put all the values here, 0.58 into F415 is the steel, grade of steel, and AST required was 402.16, and we did not change the spacing, so our AST provided was same. If you change the spacing, if you reduce the spacing, your AST provided will increase, and if you reduce, you cannot reduce the spacing, you cannot increase the spacing, but you can reduce the spacing, and if you reduce the spacing, your AST provided will increase, and the value of Fs will decrease because this ratio will decrease. So if I solve this, I get 240.7 Newton per mm square. Okay, after calculating this, we have to find out the percentage of steel in the slab, which is given as PT% equals AST upon B into D multiplied by 100. Our AST value was 402.16 upon B is 1000 again for meter width, and 125 is the effective depth multiplied by 100. If we solve this, we get 0.19%. Now we have the percentage of steel and we have the Fs value. Now I'll show you how to use the graph from the IS code. It is given on the page number 38. This is what the graph looks like. So if you see, let me zoom on this. On the x-axis the percentage of steel is given, and on the y-axis the modification factor is given. Now our percentage of steel is 0.19%, so that is around 2%, 0.2%, and that is somewhere over here. Okay, now and our Fs value is 240.7, which is the second curve from the bottom. Now I will go upwards along the 0.2% line. As we go up, check where it meets with the 240 Newton per mm square curve. So it meets somewhere here. If you draw a horizontal line over to the y-axis, you will get the modification factor for that value. So in this case it is something 1.7. okay, once you get the modification factor, you write it down on the page. Now you have the modification factor. Now you again back calculate the effective depth by using the span by depth ratio. D is equal to span upon 20 into mf. Again 20 is for the simply supported slab, which is 3000 upon 20 into 1.7. So if you solve this, you will get 88.23 mm. Now our effective depth which we used was 125 mm, and this is less than 125 mm, and hence our slab is safe in deflection. In any case, if your depth calculated from the graph from using the modification factor from the graph is greater than your effective depth which you choose, so in that case your slab will not be safe in deflection. Since 88.23 is less than 125 mm, it is safe. Once you're done with the deflection check, the second check is the check for shear, and it is given in clause number 40.2.1.1. It is on page number 72. So the shear check is somewhat similar to singly reinforced beam. There is a little bit of difference here. I'll show you what is the difference. First, for calculating the nominal shear stress, we have to find out the shear force, which is given as 1.5 W into L by 2, and 1.5 is the partial safety factor. 1.5 multiplied by 9.25 was the load, again 3 meter was the span, upon 2 you get as 2.81 kilonewton. Now your shear stress would be V upon B into D, 20.81 into 10 raised to 3 upon 1000 into 125, 0.16 Newton per mm square. Okay, now you have to calculate the tau c value. For tau c, you will have to calculate the percentage of steel. Now in the earlier case, in the deflection check, we got percentage of steel as 0.19%. That was for the central part of the slab, but at the support, your reinforcement is reduced by 50%. So you have to divide the percentage of steel by 2. So in earlier it was 0.19%. So at the support, it will be divided by 2, which is 0.095%. Now again we will use the table given in the IS code on page number 73. I'll show you that. Now for PT percent is given here, and the grade of concrete is given here. For PT percent 0.095, it is less than 0.15, which so we will use the first line over here. And for M20 grade of concrete, it is 0.28 Newton per mm square. Okay, so we'll write it down. Tau c is equal to 0.28 Newton per mm square. Now the major difference here is you have to use a table given on page number 72 for slabs, which is this one. Now for 150 mm depth of slab, the K value is 1.3. So what the clause says, for solid slabs, the design shear strength for concrete shall be K into tau c, where K has the values given below. So whatever tau c value you get, you have to multiply it by the K. Therefore K tau c is equal to 1.3 multiplied by 0.28 Newton per mm square. So which is 0.36 Newton per mm square. Now your tau V value is less than K into tau c value, so your slab is safe in shear. Tau V is less than K into tau c, therefore safe in shear. After the shear check, the third check is development length check. It is given in IS code on page number 44, clause number 26.2.3.3. It says that M upon V plus L0 should be greater than the development length. This is the moment, this is the shear force, and this is the length available from the center of the support to the face of the support, which should be greater than LD. I'll show you what is the formula for LD. The formula for LD is also given on page number 42 in clause number 26.2.1. LD is given as phi into 0.87 Fy upon 4 tau BD, clause number 26.2.1. okay, page number 42. Now just you have to simply put the values here. This is the diameter of the bar, Fy is the grade of steel, and tau BD is the bond stress. It is also given in the IS code. So I'll put all the values here. 0.87 into 415 upon 4 into. Now tau BD is calculated on the basis of the is found from the table which is given in the IS code on page number 43. So this is the table. The grades of concrete is given here, and this is the bond stress given in the second line. Now for M20 grade of concrete, it is 1.2, so we will choose tau BD as 1.2. But keep in mind, in the line below the table it is given that for deformed bars conforming to IS 1786 these values shall be increased by 60%. What it means to say is, if your grade of steel is greater than 250, that is Fe415 or Fe500, you have to multiply this value by 1.6, that is increase it by 60%. So 4 into 1.6 multiplied by 1.2, so your development length is 470.11 mm. Okay, now your M is 16.93 into 10 raised to 6 and shear force is 20.18 into 10 raised to 3 plus L0, which is 838.94, which is already greater than LD. So yes, slab is safe in development length. But these were the checks, and finally before we finish the problem there is one last thing we have to find out, that is the area of steel required for distribution bars. So we can provide minimum steel for distribution bars, and for slab for distribution bars it is given as AST is equal to 0.15 upon 100 into B into D, that is it should be 0.15% of the cross sectional area, which is equal to 0.15 upon 100 and multiplied by B, that is 1000 multiplied by 125, and this is for Fe250 steel, and for Fe415 steel, or that is HYSD bars, Fe415 or Fe500, it is 0.12 upon 100 multiplied by B into D. So let's provide Fe415 steel bars, forget about this. 0.12 upon 100 will provide 8 mm torr steel bars. Okay, 1000 multiplied by 125, so that is 150 mm square. Now for spacing for this is given as spacing is equal to area of one bar upon ASTD, that is for distribution steel, multiplied by the unit width of the slab, that is 1 meter. Okay, so area of one bar is pi by 4 into 8 square upon ASTD, which is 150 multiplied by 1000. So your spacing is 335.10 mm. Now the maximum spacing is given as 5D or 450 mm. 5 times D would be, you can calculate what is it, and 450 mm. So our value is 335 mm, which is less than these two values, so we will provide 335 mm. Okay, after doing all of that, you can finally draw the cross sectional diagram of the slab. And so this is the effective length, 3.125 meter. I have shown it from center to center of the supports, and this is the effective depth, this is the total depth. The bottom bars is the main reinforcement, that is 10 torr at 195 mm center to center, and just above it we have placed distribution bars, 8 torr at 300 mm center to center. As we all know, we bent up the bar at the supports, so alternate bars are bent up. For example, if this is the this is one of the reinforcement, just next to it the bar will be bent up, so this part won't go into the support but it will go over the support. Similarly, this bar will go straight over here, the bar just next to it will be bent up from here but it will be straight throughout this length. Okay, that's all with the design of one-way slab. I hope you liked the video, and if you have any doubts please comment down below and I'll answer them. That's it. I hope you liked the video. Please share it and don't forget to subscribe to the channel. Thank you very much for watching the video.